Start recording. Cool. All right. So we talked about, in the last section, we talked about gases and how gases work and how they interact and the fact that they're made up mostly of empty space, that we make a lot of assumptions because it makes our life easier, the kinetic molecular theory. And that's where a lot of reactions happen are in gases. And so some of the earliest chemistry that was around came about with gases. The other type of thing that we care about a lot is aqueous solutions. And the fact that these particles, like individual particles bouncing around in mostly empty space with gas, we have these individual particles moving around inside of solutions. If you will remember, we have these different terms. We have aqueous and liquid and gas. Y'all remember those terms? We have the AQ and liquid and gas and solid, right? Y'all remember those? I know a few of us may have actually slept since the last time we learned that. I think we had Christmas. Some of us. All right, here we go. We got AQ, liquid, yeah, solid. All right. So we've talked about liquid, gas, and solid probably since y'all were in second grade. Now we're going to talk about things that are aqueous. So water is a fairly unique compound. We want to talk about the Lewis dot structure. Can y'all draw the Lewis dot structure of water? Y'all should go ahead and do that right now. What's its shape going to be, molecular shape? It's going to be bent. So I've got my oxygen, my hydrogen. That's your Lewis dot structure. Let's see if I can find it again. What's that? Yep. So remember, these are two-dimensional drawings representing things in three-dimensional space. So if I'm looking at this, this is what this looks like. Okay? But in three-dimensional space, it's going to look bent. And oftentimes, we will draw this another way. They are both equally accurate. Let's draw it like this. Okay? And that's when it looks like this. You guys can kind of see the shadows there, right? Okay, so that's this one, and that's this one. The electronegativity for oxygen is very high at 3.5. This is a very polar molecule. It has a very unique property that between water molecules you can have a very special kind of bond called what? Hydrogen bonds. I can have hydrogen bonds between these two. That's what lets us have, when we pour that glass of water and we pour a little extra and we can put that little, right. And that's what forms the meniscus in the graduated cylinders when we're measuring. That's that curve there. Hydrogen bonding. That's what lets things like, spiders walk across the surface of the water. If you've ever done that trick where you float a paperclip on top of the water, all that's done because of hydrogen bonding. This all has to do with the intermolecular forces, right? The forces between molecules. That's an H bond. To be clear, this bond here is what kind of a bond? It is a single bond. All right, so we have a bond between like sodium and chloride. We're going to call that a... So this is a covalent bond. And in particular, because this is 3.5 and this is 2.1, this is a what kind of covalent? This is a polar covalent bond. That's a polar covalent bond. So I want to be clear that you guys understand these different pieces of this. You need to understand water before you can understand solutions. If you can think about water as you work through these, they're kind of like the empty space of gases. Generally speaking, when we talk about aqueous solutions, I don't care about the water itself. A little later on, we talk about acids and bases. We'll start caring a little bit about the water. But generally speaking, I don't care about the water. The water is just there so that the particles I do care about have something to move around in. And part of what they're doing is the hydrogen bonding, and whether the water molecules are bonding to those other particles or they're just interacting with themselves and excluding those other particles. So we'll talk about that. This hydrogen bonding is what explains the high boiling point. I mean, for a little bitty baby molecule, right, what's the molar mass of water?
18.016.
Yeah, good, 18.016. That's a little bitty molecule. And yet it boils at 100 degrees Celsius. Let's compare that to carbon dioxide. Carbon dioxide's got a molar mass of what?
Say it again. 34.06. 12.01 plus 16 times 2.
Yeah, so 44. So carbon dioxide has got a molar mass of basically 44 grams per mole. And yet its boiling point is minus 80 degrees Celsius. Okay? And the reason for that is, what kind of intermolecular forces does it have? Is it polar or nonpolar? It's nonpolar. And a nonpolar molecule can only have what kind of intermolecular forces? London dispersion forces. Very weak, intermittent forces, London dispersion forces. So even though it's bigger, it's got much weaker forces, so it boils at a much lower temperature. Okay, so that's what makes water impressive. All right. There we go. All right. So we've got a temperature here. I want you to understand the density of water. Typically, we're going to say the density of water is, what have y'all been taught since 5th grade? 1. That's a lie. Just be used to that. You should be used to it by now. It's only 1 at 4 degrees. Water's maximum density is reached at 4 degrees. Below 4 degrees, it actually becomes less dense. And if you get down to 0 degrees liquid, really no difference. But as it becomes a solid, it actually does what? It expands. This explains why you don't put glass bottles in the freezer, and why your mama yells at you when you leave your soda can in the freezer. And it does what? It explodes. It blows up all over the place, right? This is a significant difference.
So it's like an exponential.
Well, it definitely expands a significant amount. Okay? Most other chemicals, as you get colder, they get more dense. Water is unique, and again, it comes down to these hydrogen bonds.
What about another, like, hydrogen bonded thing? Like, let's say oxygen, or not hydrogen and like fluoride. Would that, like...
So that's not going to do that, and I'll show you why in just a second. We're going to show a pretty picture here. But at 4 degrees, notice I can heat this and heat this and heat this until I get to like 50 degrees. I really don't notice any difference. We tend to do a lot of lab work at 25 degrees, which is a bit warmer than this room right now, which our little 19 degree, 20 degree room right now. And so 0.9971 is pretty close to 1. So if you're pouring water in the lab, it's fine, it's 1. Don't have to worry about it. Now, as you get up to 50 degrees and 100 degrees, that starts making a difference. But notice, it's still less dense as ice than it is as water that's just about to boil. So be aware of that. Okay, good. We are still recording. Here's what's going on. Ice forms these open networks, forms these rings here, these structures where everybody's bonded to everybody else. It swings out. In order for those hydrogen bonds to happen, the water molecules must take up more space. And there's a cool little video we may watch next week talking about this, how ice actually forms, and it shows some nice stuff on that. We have some partial hydrogen bonds here. This is still water. Notice how you've got a bunch of empty space here. And this is what causes your ice to expand as it forms.
This is when it's ice.
This is ice right here. These open networks. So you got 1, 2, 3, 4, 5, 6. What's that? Yeah, and we've got partial bonds. Some of them are swinging. They're open. You've got some hydrogen bonds, but not everybody's hydrogen bonded. By the time you get to ice, everybody's, more or less, everybody's hydrogen bonded. Okay? So keep this in mind. The structure of water, so that the molecule you mentioned doesn't have that structure, right? It's a linear. So it's not going to create this kind of shape. Good? All right. Unfortunately, there is math in this unit. There's also a lot of vocabulary that can be confusing. So, aqueous solutions have two parts. The solution is made up of the solvent and the solute. The solvent is the dissolving medium. It's the one that's in greater amount. Typically, we're talking about water. Typically, that's water we're talking about. We good there? This doesn't have to be water. And the solute is the substance being dissolved, the substance in the lesser amount. Typically, when we're talking about it, we're talking about in terms of a solid. So the idea that I can take solid salt or solid sugar and mix it into water, we're making a solution. All right. This happens through a process called solvation. Yeah, I know. Scientists and our vocabularies, really. Okay. This is something that's on your notes. I want y'all to start thinking through this and thinking beyond this. Prediction of whether solubility happens. Again, the question is, will something dissolve in water? Or will it dissolve at all? You want to ask, is the substance, is the solvent polar? And is the solute polar? If they're both polar, they will dissolve. If they're both nonpolar, they will dissolve. A simple way for you to remember this is this phrase, like dissolves like. However, I want your brain to be thinking in these terms. In other words, when we start doing free response questions, I don't ever want to see this written down. What this means is water is a polar compound. So, polar solutes will dissolve in water. This is why it's really important for you to reach back, know how to draw Lewis dot structures, and know how to figure out if something's polar or not. Make sense? If I ask you, will this dissolve in water, you're going to need to figure out if it's polar. And the way you figure out if it's polar is to write the Lewis dot structure. So, ionic compounds, they're going to be soluble to some degree. And we're going to be talking about solubility rules.
No.
pretty straightforward. We looked at them, I think, last semester, or at least earlier this year at some point. Remember when ionic compounds dissolve in water, they tend to form electrolytes at some level. Polar covalent, an example of that, let's talk about an example. This would be like salt. The salt that we all eat on our French fries. Okay. If I put salt into water, it fully dissociates, breaks up into those ions, and I can transmit electricity. Polar covalent. Sugar. Okay. So sucrose, the stuff we use to sweeten our coffee or tea or whatever, mix that in there. That does not dissociate. And because it doesn't dissociate, it means I don't have any ions. And because I don't have any ions, it's not an electrolyte. Again, it's important now, it's important for you guys to be able to determine whether something is an ionic compound or a covalent compound. A non-polar covalent is not going to be soluble in water. Okay? Methane would be an example of that. CH4, yeah. Or we could even do, one of these other things, C4H8. Any of those things, those are going to be non-polar covalent. And they too are non-electrolytes. Covalents are not so notice the covalent, right? Covalent tells me it's not going to be an electrolyte. It doesn't have any ions. So, question here, can I make an aqueous solution with carbon tetrachloride? Draw the Lewis dot structure, everybody.
So we're looking at the solubility of the compound or the bond itself?
So you want to look at you need to find out if the compound's going to be polar or non-polar.
Okay, so like, because I remembered that one rule that if it's like carbon and then 2 chlorine and then like 2 hydrogen, it'd be non-polar.
Well, it'll be polar, right?
Other way around.
Other way around. So let's go ahead and look at this. This is going to be carbon.
Yeah, this is
So I've got carbon. All right. We got two questions. Do I have any lone pairs in the middle? No. Is anybody different? All right, so no, non-polar. So this is non-polar. If it's non-polar, is it going to dissolve in water? No. So that's not going to happen. But the question that was just raised, let's look at if it is carbon. Okay? H. Is this going to be polar or non-polar? Polar. It's going to be polar. Is it going to dissolve? Yeah, this is going to be soluble because water is polar. Okay? That means this is polar. It's going to form a dipole. So I'm going to have dipole-dipole interactions between this and the water. The only attraction I'm going to have between this and water are LDF. The reason this doesn't dissolve, though, is all those water molecules have a very strong hydrogen bond with the other water molecules. What happens is the water molecules all get together and exclude this guy. Push him out of the way. You're in the way of a nice, favorable hydrogen bond with another water molecule, so these guys get pushed out of the way, and they all have to hang out by themselves. Whereas this guy says, I'm going to be friends with some of you because you can make a dipole-dipole interaction. Because this part of the molecule will be more negative, and this part will be slightly positive.
So the reason they don't want to, they don't bond is because they're too, bonded to each other.
Exactly. In this case, the water molecules are too bonded to each other.
Just in that case?
Well, in this case, they're going to be they're going to be bonded to each other, but they're also going to have some bonds to these guys. Remember, as a water, some of them weren't fully bonded.
But what if that was what if it was a different element than hydrogen?
Well, if it was something that made it positive, right? So it could be, it couldn't really be, well, we could do this. So we could do something like this.
Because you said that the reason it would bond to that was because it's like hydrogen and they want to bond with other hydrogen.
No, positive, slightly positive.
Okay.
It has nothing to do with the hydrogen. It has to do with the difference in electronegativity. All right. So an electrolyte. This is the definition I need you to know. It's not the one you get on the Gatorade commercials, right? This is a compound that conducts an electric current in the aqueous or the molten state. So come visit me next year and I will melt some salt for you. Okay? It takes a bit of high temperature and to actually melt salt. But if you melt salt, it will conduct electricity. And if you take a little bit of salt, much easier, put some salt, just a little bit, into water, it will conduct electricity. Yeah?
When you cook, does that melt salt?
When you do what?
When you cook things?
That is typically you're not cooking with a temperature high enough to melt salt. In fact, that's a good point. One of the ways, if you ever are faced with this situation, you come into the kitchen and you have two bowls of this granulated white substance, and you know one of them's salt and one of them's sugar. You can take a frying pan, put it on the stove, and turn it on. And if you put the salt on, pretty much nothing's going to happen. Put the sugar on. Any of y'all ever burn sugar?
No.
Yeah, it's kind of nasty and gross. Oftentimes. So, well, but maybe you want to be a little more precise. Maybe you don't want to taste it, right? But you could do that, right? You could pour that on, and it'll melt, and it'll turn black, and
Then you get to clean it up.
you get to clean it up.
So I would just taste it.
I didn't know that happened with sugar.
So sugar breaks down, right? It's a covalent bond. It requires less energy to break covalent bonds than it does ionic bonds.
I don't cook that, so.
What?
Salt turns electric when you melt it?
So when I melt it, it conducts electricity. So I can put a positive in one side and a negative in the other, and electricity will flow between them.
Wait,
So that's why there's this King of Random video. I'll post it up on Canvas. Y'all can watch. It's really kind of fun. It's one of the reasons you talk about don't have your toaster in the bathroom in case it falls in the bathtub, right? Don't blow dry your hair while you're taking a shower.
what?
Yeah, it's kind of fun. It's kind of funny because they had to tell my generation these things, and somehow y'all figured that out. Don't blow dry your hair while. I guess you're in the bath. Anyway, we talked about that all the time. Like,
So you said when you burn or you melt salt, it forms an electric current. So that can be used in the what's it called? You could use it as a wire or something
yeah, it conducts electricity. Yeah, it doesn't make its own electricity. It just conducts whatever you do to it.
But it could be used as a wire.
If you want to keep it molten, yeah. But solid salt does not conduct electricity because there's no mobile ions.
This is why you put it in water.
So you put it in water, the whole bunch of water molecules come together, break those guys up, and now I have these positive and negative charges just floating about, and they can transfer electricity.
Let's say you had a little insulated piece of wire, but instead of metal, you had salt and water. Would that actually work?
Uh-huh. Yeah, we actually will do something similar to that in AP, yeah.
Why don't they use something like that instead of copper?
It's incredibly inefficient, and copper's all the electrons are lined up next to each other, because copper, if you remember, is a metal, and so you've got the cores surrounded by a whole bunch of electrons, right?
It would settle too with the salt.
Probably not, but water will dissolve. right? So if you broke the container, then your power lines would have no, because it would go back to solid salt, which doesn't conduct. It's an insulator. So, yeah. All right. So keep that in mind here. All right. Let's talk about solubility. Solubility is listed as the number of grams of solute that dissolves in a given quantity of solvent, usually 100 grams. Notice, grams is what I said here. Nice thing is, I know that a milliliter of water is how many grams?
A milliliter of water is how many grams?
Uh-huh.
Oh, wait. At 4 degrees is
1. Yeah. 1 gram, 1 milliliter. Yeah. At 4 degrees, but we also, in laboratory conditions that we're going to be using, we're going to consider it the same. All right. Factors that involve solubility. So how much could I possibly dissolve? How much is it that I could possibly dissolve? Well, temperature. Temperature. And we'll see if we have time for this. I have a feeling we won't, but we'll see if we have time to do a quick little solubility lab. We know that if I'm talking about solids, as I make it warmer, I can dissolve more. So those of you who have who enjoy warm coffee, you can put more sugar in that more easily than you can if you do a cold coffee. Or iced tea. Growing up, we had these big potluck luncheons, and we would have in the little kitchen, we'd have these 5-gallon. I'm not kidding, 5-gallon steel. I guess they're probably cast aluminum, and we'd be boiling water to make the tea. And the people who were cooking would just take scoops of sugar. We had another big bucket of sugar and just scoop it in there and stir. And scoop it in there and stir, and that's how we made our tea. Well, it's a lot easier to dissolve sugar in the tea while it's still warm than it is after it's cold. A lot of y'all have gotten your iced tea and you've gotten it at your table, you set it down, you put your little sugar in it and you stir and all the little particles fall to the bottom, right? But if that tea was warm, you don't even have to stir it a lot of times, right? You just put that little sugar in there and it just dissolves. And that has to do with the movement of the water particles taking apart the sucrose crystals. The nature of the solute or the solvent, and we just sort of talked about that. Ionic and polar covalent compounds will dissolve in water, and nonpolar covalent do not dissolve in water. Good. All right, question. How do I figure out if something's a solvent or a solute? Is there a metal in the formula? In other words, is it going to be a metal or not, and a non-metal? Ionic? If it's 2 nonmetals, we're going to say it's covalent. Thank you. Okay. For covalence, I'm going to have to draw the Lewis dot structure. If it's not one that I just already know, I'm going to need to draw the Lewis dot structure and figure out whether or not it's polar. And you figure out whether or not it's polar by just asking those 2 questions. Are there any lone pairs in the central atom? And if not, is there anybody different? Good? Got that? All right. Pressure. For gases only. For gases only. We frequently have questions on the test, and students get confused about this. Pressure And what I mean by pressure is the pressure that's on top, this space here. Because we know we can compress gases, right? But we can't compress liquids and solids. So when I'm talking about pressure, I'm talking about the pressure pushing down onto the top of the liquid. So for example, in soda bottles, oftentimes you'll have about 5 atmospheres, which is a significant amount, pressure of carbon dioxide being forced in there. So this space right here is about 5 atmospheres. This is why when I open a soda bottle and bring it out to the atmosphere, what's it? Partial pressures like here's what, point something. We learned it last time and I'm forgetting it off the top of my head. Say it's 0.1, okay, for CO2. What that means is the CO2 is going to leave your soda and go out into the atmosphere because it's trying to form an equilibrium. And what that's going to taste like to you is a flat soda. But why your soda stays carbonated when it's in the bottle is because it's sealed up here. And this soda, this carbon dioxide is being trapped in the headspace. That's what that's called. Okay? But remember, more pressure, more solubility, only for gases. There we go. Only for gases. All right. So that is solubility. That's how much I can dissolve. My next thing I want to look at is how fast it dissolves. So, in simple terms, heat, crush, stir. Stirring. The fancy Nancy word for stirring is agitation. This works because the water molecules are being brought past the solute. More of them are being brought past the solute. Therefore, they can participate in solvation and break up the individual molecules or atoms, depending upon what it is we're talking about. Temperature. If I raise the temperature, I have more kinetic energy. Those water molecules are moving faster and faster. So we talked about this with gas, that the temperature of the gas is directly proportional to the temperature in Kelvin. This is actually true for most things. More kinetic energy, more collisions, more movement. Particle size. If I start out with a smaller particle, that means there's more surface area. That means those individual atoms or molecules are exposed to the water more quickly and therefore can enter into solution more quickly. So the quick way to remember it is heat, crush, stir, but you need to remember what those mean. More words you need to know. Miscible, if 2 liquids dissolve into each other. So this was like, an example of this would be water and alcohol. So let's take a look. Let me go get a marker that shows up. So water is H2O. And alcohol, let's look at a simple one. Okay, water is polar, yes? And alcohol is polar? Yep, because this is going to look like this. Okay, so it'll be polar. Water is also polar, so this is going to be dipoles. It's going to form some dipole-dipole. It's actually going to form not just dipole-dipole, it's actually going to form what? It's actually going to form hydrogen bonds. This going to form here. Okay? And form some nice little hydrogen bonds there. Oil and water. Right? Any of y'all ever had the salad dressing? Vinegar and oil, salad dressing, right? You have to shake it up. And even then, if you just let it sit, what happens? It looks like this, right? Because that vinegar is acetic acid, and so that's mostly water, and it's going to separate out. Those guys are going to stick to each other. The oil is going to be less dense. It's going to raise to the top. and they're going to be separated. All right.
Is it the more dense? The more dense one goes on the bottom, right?
Correct. Okay, so miscible and immiscible. And yes, I know there is math on this test, but there's a lot of vocabulary you got to keep up with. What's that? Yeah, there's actually a quiz that's out there. You know. So those are good things.
I studied for this. We'll see about that when you get your degree.
So hopefully, we may do some quizzes as too, kind of like those. Oh yeah. Yeah, agitation, temperature, particle size. Let's throw some more vocabulary in there for today. A saturated solution. A saturated solution has, the water is holding as much as it possibly can hold.
Is that ever truly going to happen?
Oh yeah, all the time.
No, but like 100%.
What we were
Uh-huh.
talking about?
Every single molecule.
So what we're talking about is the capacity of a, so I say I'm going to have a glass of water at 25 degrees Celsius, a glass of water at 25 degrees Celsius. I can dissolve a certain amount of sugar. After that, any more sugar I put in just falls to the bottom. It's not in solution. I can actually do that for lots of these. An unsaturated solution contains less than the maximum. And a super saturated solution contains more solute than it should be able to.
So is that why it sinks to the bottom?
No, this is actually a different scenario. So this is a scenario where I heat it, and so the capacity for that solution increases.
It actually increases.
And so these particles, they spread out. I can stick some more solute molecules around the solvent molecules, and then I very slowly let it cool back down. And if I'm careful enough, basically as those water molecules slow down, the solute particles stay away from each other.
Which is why when you put sugar in tea and then cool it down.
Yeah, that's yeah, sort of similar to that. And we can. Well, I'm definitely going to be showing you some examples of this. So, crystallization is not going to occur. All right. If I shock it, and in fact we do this, we take a supersaturated solution, and you actually shock it. You just prime it a little bit. It'll form the whole thing will crystallize really rapidly. And I've actually got some reusable hand warmers that use that process. In fact, let me see if I got any that are. Oh, I do have a couple. So these are supersaturated solutions. Can y'all see that these are liquids?
I want to see.
So these are liquids.
Wait, pass it to me.
Okay, I've got another one for you. Okay, it's a hand warmer. This is a supersaturated solution. It's a liquid. And I'm going to activate it.
Yeah, I can touch it.
And now that forms a crystal.
Oh, it's like when you put your finger in the water after it's been in the freezer. Have y'all never done that?
It's like reactivated ice block.
Yeah, it's similar, except it's.
What the heck? That's not even warm.
You leave your water in the
That's
fridge
so
for 2 hours and you touch it with your
Yes.
finger.
So where'd you get
That is.
Is that
I got them on eBay.
Feel it.
And so yeah, so these are liquid. They're supersaturated. And this is a great example that shows you that freezing is an exothermic process. In order for something to freeze, it has to give off heat.
Why is it so long? Wait,
Yeah, it is
so
super
it
weird.
Thanks for explaining that, because I didn't know.
Yeah.
Can you go back a slide for a second? I just realized that.
Are miscible and immiscible.
Let me write down my name.
where were those?
Super
Where
weird.
were those when I needed them? It's cold.
Where were we?
Wait, I thought it was cold. It's hot?
What?
Well, he just said they were hand warmers.
Oh.
But it's going from a liquid to a solid. In order to go from a liquid to a solid, it has to lose energy. And it loses energy by pushing heat into the environment.
Oh, are we like passing around?
That's COVID, guys.
Well, I guess you'll have COVID now.
Oh,
Why are we passing them?
it's kind of cold.
I don't know.
I feel like this looks like a body function.
Huh? Bro, you just dropped the function.
I don't think that was the right term.
It's not function,
Process.
No.
looks like a bugger, bro.
There you go.
Why did you say that?
So I was just trying to use a scientific word.
Wait, whoa!
That one looks
Is
worse.
that the yellow one? I want to see.
That looks like.
That's so cool.
So you take that.
Now that looks like a
Wait,
So you can pop it against the table, or you can pop that.
pop it like did it?
Yeah, I just crack this. Take this
Did you get new scrubs?
and pop it like
No, I
that.
always had that.
All right.
Hasn't been drinking.
Evidences of. Nope, we're not doing that.
Go back.
Which one? This one?
No. Keep going forward.
Oh my god, it just got hot.
Keep
It's so
going.
cool. Where did you get these?
eBay.
Next one.
Wait,
All right.
it got so hot so fast.
Right.
That is so
They make
cool.
large versions of them. Who's Cadence? Let me see that.
This?
good
I
catch.
spelled solid wrong.
All right. Let's remember what some evidences of chemical changes are. We do color change. We produce a gas or a solid, a precipitate. That's what we're talking about today. Energy change. Almost all chemical reactions have an energy change. Almost all chemical reactions have an energy change. We could have a new odor or a change in odor. Okay, evidence of a chemical reaction. We typically write these as a chemical equation. We've been doing this for a while. And we typically put the reactants on the left side and the products on the right side. And we have an arrow that says we move from reactants to products. Here's our symbols. Again, we've done this before, but I want to make sure we're going to go over it again. This is our plus, so if I'm reading a word problem, I would say, water reacts with X to produce something else. This is our yields, produces. This says heat's been added. You're not going to see this very often, nor are you going to see this. Okay, you may see it later on. I don't think you're going to see it this year. You may see it once or twice next year. This is one that you're going to be we're going to use a lot. And that's to recognize that many, many chemical reactions are reversible. They can go back and forth. Do be aware, solid, liquid, and gas. Aqueous, this is a solution. When I say something's aqueous, what I'm saying is it's surrounded by water molecules. It's not interacting with the water molecules, but it's surrounded by them. So if I say NaCl, and I write aqueous next to it, what that tells you is this is salt that's in water. And so the reality is this looks like this. There's some Na ions floating around and some chloride ions floating around. All right? That's what that means. If I just say Na and I say solid, NaCl solid, that's the stuff that's still in your salt shaker. Nothing's happened yet.
So when it's aqueous, is the solution broken apart?
Yep. If it can be. Now there's stuff that's, if I say sugar or whatever, it would be a polar, something like that that's polar. I would say aqueous. Typically, we're talking about one of the salts, and they're broken up. But all we're saying when I say aqueous is it's surrounded by water. So keep that in mind. Yeah, and we're done. I'm going to stop there.
Can you go back to like the beginning so I can do all the math?
Oh, just kidding.